Welcome to the video lecture on power series and interval of convergence. Now we've learned that functions can be approximated by a Taylor or Maclaurin polynomial, and we saw that the higher the degree of the polynomial, the better the approximation became. In this section we learned that several of these functions can be represented exactly by an infinite series called a power series. So here's our definition of a power series. If x is a variable, then an infinite series of the form a sub n x to the n from 0 to infinity, which would expand into a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed and so on, is called a power series. In general, you can have a series that's centered at any value c. So you can take a series of the form a sub n parentheses x minus c to the n, which would be a sub 0 plus a sub 1 x minus c plus a sub 2 x minus c squared and so forth. And this is a power series centered at c. Now a power series can be viewed as a function. It's a function of x, having as its domain the values of x which make the power series converge. So what does it take for a power series to converge? Well, there's three possibilities. For a power series centered at c, precisely one of the following is true. Number one, either the series converges only at c. Number two, there exists a real number r greater than 0 such that the series converges absolutely for the absolute value of x minus c less than r and diverges for the absolute value of x minus c greater than r. Or the third case is that the series converges absolutely for all x. This number r is called the radius of convergence. So in the first case, if you only converge at a specific number c, then we say that your radius of convergence is just 0. In the second case, if you converge for values of r that satisfy the absolute value of x minus c less than r, then r is going to be a specific number that you will solve for in the problem. And in the third case, if you converge absolutely for all x's, then that means you converge for everything, so your radius of convergence is going to be infinity. Now the set of all values of x for which the power series converges is called the interval of convergence. So this video lecture is going to focus on finding the radius of convergence and the interval of convergence for different power series. Now when you're trying to find the radius of convergence, you always want to use the ratio test. And if you're trying to find an interval of convergence, after you've found this radius, what you're going to do is check your endpoints independently to determine your interval of convergence. Now just as a reminder, what the ratio test tells us is that a series is going to converge if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. So we're going to force this condition, this limit, to be true in order to determine what our radius of convergence is. So let's take a look at our first series. We've got the series 4x raised to the n as n goes from 0 to infinity. Now just to get a feel for what this looks like if you were to expand it out. If n was 0, anything to the 0 is just 1. If n is 1, then this is just going to be 4x to the first. If n is 2, then this will be 4x squared. If n is 3, this will be 4x cubed, and so forth. So that's an infinite series, and it's kind of like an infinite polynomial. Okay? So to determine what this is going to have for its radius of convergence, we're going to apply the ratio test to this series. So we're going to look at the limit as n goes to infinity of the absolute value of the nth plus 1 term over the nth term, and we want that to be less than 1 in the end. So what would the nth plus 1 term look like? Well, this is your nth term right here. So the nth plus 1 term will just be all of that 4x raised to the n plus 1. So the nth term would just be 4x raised to the n. Now to simplify this a little bit, notice that you can break up that exponent in the top. So this becomes 4x to the n times 4x to the first, or just 4x, over 4x to the n. So these 4x's to the n cancel out, and this just becomes the limit as n goes to infinity of the absolute value of 4x. There's no n in there, so 4x is kind of like a constant. It's not a function of n. So in the limit of a constant is that constant back again. So this limit will be the absolute value of 4x. And what we need for this to happen is we need this to be less than 1. So if we solve this inequality by just isolating that x, I'm going to go ahead and divide by 4. The number that you end up with right here is called your radius of convergence. And we'll talk about interval of convergence a little bit more in a few examples. But this inequality then says the x's that are going to make this true would be all the x's that in absolute value are less than 1/4. And that's the same as all the x's squeezed in between positive and negative 1/4. So that would be the start of our interval of convergence. And then we would need to check our endpoints separately to determine whether or not they converge or not. So that's kind of where we're headed. But for now, all we wanted here was our radius of convergence. So our radius r is 1/4. Now this series up here is centered at 0 because it was just x's raised to powers. Likewise for this next example, this is also centered at 0. And what some of the terms would look like initially, the first term when n is 0 would just be 1, and then this would be 2x over 1 factorial plus 2x squared over 2 factorial plus 2x cubed over 3 factorial, etc. So again, this is an infinite polynomial called a power series, and this one is centered at 0. So to determine where it's going to converge, where it's actually going to have a value, we're going to apply that ratio test again. So we want to look at the limit as n goes to infinity of the nth plus 1 term over the nth term. So in this example, the nth plus 1 term would be all of this with n plus 1 plugged in. So that'll be 2x to the n plus 1 over n plus 1 factorial, and we're dividing that by the nth term, which would be 2 to the x to the n over n factorial. Now we have a little bit of simplifying to do here. So what I'm going to do is I'm going to multiply by the reciprocal of this bottom fraction. So it's going to become an n factorial over a 2x to the n, and we're multiplying that by this numerator. And in this numerator, I'm going to break it up. I'm going to take that 2x to the n plus 1 and make it a 2x to the n times a 2x. I'm also going to break up the n plus 1 factorial. N plus 1 factorial is n plus 1 times n factorial, since n plus 1 factorial is bigger. It's one integer bigger. So that means I can cancel out the factorials, I can cancel out the 2x's to the n, and what I'm left with to take the limit of is a 2x on top and an n plus 1 in the bottom. And this still has an n in it. So what's going to happen to this as n goes to infinity? And you want to think of x here as basically just being a constant. So this is a fixed constant on top, and n is getting bigger and bigger in the bottom. So this is going to infinity on the bottom, and the top is fixed. So 1 over something big gets small. And that is less than 1 always, and that's what we want to happen for the ratio test. In order for convergence to happen, this value that we got for the limit has to be less than 1. So this is always convergent for all x's. So what does that mean about our radius of convergence? If it's always convergent, then our radius of convergence is infinity. Okay? For this bottom example here, let's write out a few of the terms. When n is 0, again, this is just going to be 1. When n is 1, this is going to be x to the first. When n is 2, this will be 2 factorial x squared plus 3 factorial x cubed plus 4 factorial x to the fourth, and so forth. So another infinite polynomial. This is centered at 0 because you don't have a shift here. It's not x minus something raised to the second power or x minus something raised to the third. It's just an x. So this we would say is centered at 0. And if we want to see where it converges, we're going to look at that ratio test again. So I'm going to take the limit as n goes to infinity of the nth plus 1 term over the nth term. So this becomes this formula with n plus 1 plugged in, so n plus 1 factorial times x to the n plus 1 over the nth term, which would just be n factorial times x to the n. And I'm going to do the same trick that I did on the last example. I'm going to break up that numerator. N plus 1 factorial is n plus 1 times n factorial, and x to the n plus 1 is x to the n times x. So the x to the n's cancel, the n factorials cancel, and what I'm left with here is an n plus 1 times an x, and x is like a constant. So what's going to be the limit of this as n gets big? Well, if this is getting big, then the whole thing is getting big. So this goes to infinity. So there's no way that this is going to be less than 1 except potentially at 0, the point where we are centered at. Because if x is 0, then this could become 0 and be less than 1. So this is never true. This is always going to diverge because it's going to infinity unless x is 0. So let's see what happens at 0. If we go back to this infinite polynomial and I plug in 0 for all these x's, then all these terms here will go to 0, but I'll just have this 1 out front. So this polynomial would just be the same as 1. And that will converge because it converges to 1. So this converges only at x equals to 0. And if your radius of convergence, or if your power series is only converging at a single number, then your radius of convergence is going to be 0. There's not a whole interval of values that you range between. You just are convergent at one specific number. So your radius of convergence will be considered 0. Okay, so now let's talk about interval of convergence. So we're going to start off exactly the same way that we did for the radius of convergence. You're going to start with a series like this. If n is 1, then this is positive, and we're just going to get 1 times x to the first, or x. If n is 2, now this is odd, so we'll be minus, and we'll get 2x squared, then plus 3x cubed, minus 4x to the fourth, and so on. So there's our infinite power series. Again, this is centered at 0 because there's no shift going on. So to start off with, if you want to find an interval of convergence, you're going to look at that same limit that we did earlier for radius of convergence. So the limit as n goes to infinity of a sub n plus 1 over a sub n. So a sub n plus 1, now when we're doing the ratio test, we're doing an absolute value. So that knocks out that alternating piece, and we can ignore the negative 1 to the n plus 1. So this is all I need to look at for my a sub n's. So a sub n plus 1 will be n plus 1 x to the n plus 1, and a sub n will be n x to the n. Breaking up that power on the numerator, this is going to be n plus 1 x to the n times x over n x to the n. These will cancel out. So I'm left with n plus 1 times an x over an n. Now as n goes to infinity, these are going to get larger and larger, but they're dominated by an n over n, which reduces to 1. So the n part here is going to 1 in the limit, leaving me just that 1 times x at the end. So this is going to just the absolute value of x. We need that absolute value in there still. And what we want is that in absolute value, this needs to be less than 1 in order to have convergence. So your radius of convergence would just be this 1 that we got over here. Your interval of convergence is going to start by taking a look at this interval that's mentioned by this inequality. If you want the absolute value of x to be less than 1, then that's the same as the triple inequality, negative 1 less than x less than 1. Now that's just the beginning of our interval of convergence. What we need to look at now are the endpoints. And we need to see what happens specifically if x is 1 and negative 1. So that's what I'm going to do next. So when x is 1, we're going to go back to this original series and we're going to plug in 1 for x. If I plug in a 1 right here, this just goes to 1. So all we're going to be left with is the alternating series -1 to the n plus 1 times n. And if you think about what that's going to look like, that's going to be when n is 0, this is just going to be 0. And when n is 1, this will be 1. And when n is 2, we'll get a -2 and then a +3 and then a -4 and so on. Is that going to converge? No, it fails to converge because of the nth term test for divergence. If you take the limit as n goes to infinity of this nth term right here, that's going to blow up. These terms keep getting bigger and bigger and bigger. So this diverges by the nth term test. So that means we do not want to include the endpoint at 1. We want to leave it strictly less than. So now let's see what happens at the other endpoint, -1. So if I plug in -1 for my x right here, then this is going to be -1 to the n plus 1 times n times -1 to the n. And you can simplify that a little bit. A -1 to the n plus 1 times a -1 to the n is a -1 to the 2n plus 1. You can add those powers together. And now if n is 0, this is just going to be 0. If n is 1, 2 plus 1 is 3. That's odd, so this will be a -1. If n is 2, 2 times 2 is 4, 4 plus 1 is 5, so that's odd again, so now this is going to be -2. And in fact, 2n plus 1 generates always odd numbers. So that means this is really the same as the series -n. So -3, -4, -5, and so on. Is that going to converge or diverge? This diverges, again, because of that nth term test. These terms are not getting smaller. The n is going to blow up to infinity because of that nth term test. So we have a divergent series at both of our endpoints. So that means our interval of convergence is just going to be strictly between -1 and 1. And usually we write it in interval notation. Okay? Let's try another example here. So here we have the series -1 to the n, x to the n over n plus 1 times n plus 2. So to start off with, to find that interval of convergence, we're going to start with our ratio test again and take the limit as n goes to infinity of a sub n plus 1 over a sub n. That's going to knock out the alternating piece because of the absolute value. So we'll just get an x to the n plus 1 over n plus 2 times n plus 3 when I plug in n plus 1's here and here. And on the bottom for a sub n, I'll just get x to the n over n plus 1, n plus 2. So multiplying by the reciprocal and doing some reducing here, if I flip this bottom over, it's going to be an n plus 1, n plus 2 over an x to the n. If I break this numerator up, it's an x to the n times x, and then the n plus 2, n plus 3 stays put. So the n plus 2's cancel, the x to the n's cancel, and we're left with the limit as n goes to infinity of an x times an n plus 1 over an n plus 3. So what happens to that as n goes to infinity? Well, these dominant terms, n over n, are going to go to 1. So again, just like in the last example, this is going to leave us with just that absolute value of x times 1. And we need this to be less than 1 in order to have convergence. So again, my radius of convergence would be 1, and initially my interval of convergence is going to be all the x's between -1 and +1. But we have to check the endpoints. So let's see what happens at 1. So I'm going to plug in a 1 right here. Now 1 to the n is just a 1, so this part I can just ignore. It's going to go to just a 1. So we're left with a -1 to the n on top by itself and an n plus 1 times an n plus 2 on the bottom. Now does that converge? Hopefully by now you're starting to get the hang of your series tests, and this one, because it's alternating, would be a good candidate for the alternating series test. So if I use that, I would need to look at the limit of the nth term, which would be 1 over this n plus 1, n plus 2. And as n gets big, this denominator gets big, so the fraction gets smaller. So this will go to 0, which is what we need. The other condition that we need is that a sub n plus 1 needs to be less than or equal to a sub n. Well, a sub n plus 1 is 1 over n plus 2 times n plus 3, and a sub n is 1 over n plus 1 times n plus 2. And this is true because these two denominators are bigger than these two, so the fraction as a whole is smaller. So this condition is true as well. That means we have convergence by the alternating series test, and that happened at 1, so that means I do want to include the endpoint 1. So now let's see what happens at negative 1. So now I'm going to go back to here, and I'm going to plug in a negative 1 right here. So this would become negative 1 to the n times another negative 1 to the n over n plus 1, n plus 2. Now think about that. Negative 1 to the n times negative 1 to the n, they have the same power, so you can combine them. And this would be negative 1 times negative 1, which is positive 1 to the n, which is just 1. So the two numerators on the top actually cancel each other out. So this is really just the series 1 over n plus 1 times n plus 2. Now, does that converge or diverge? You hopefully can see that it's kind of acting like the series 1 over n squared, which we know converges because it's a p-series. If we do a limit comparison test using this 1 over n squared, then what we'll see is that in the limit, we're going to get the unknown series on top divided by the known series, and when I multiply by the reciprocal, this gives me an n squared on top and an n plus 1 over an n plus 2, and that goes to 1 in the limit because it's an n squared over an n squared. And what we need is for that to be greater than 0. So we have convergence because our known series converged, and that means x equals to negative 1 worked, so I want to include it. So my interval of convergence is going to be bracket negative 1 up to 1 bracket. All right, let's try another example. So now my series is negative 1 to the n factorial x minus 4 to the n over 3 to the n. So if you expand this out a little bit just to see what some of these terms are going to look like, you would let n be 0, which is going to make all of this go to just 1, because you'll get 0 factorial, which is 1, x minus 4 to the 0, which is 1, and 3 to the 0, which is 1. If n is 1, then this is going to be odd, so this will be negative 1 factorial, x minus 4 to the first over 3 to the first. If x is 2, then we get 2 factorial, x minus 4 squared over 3 squared, and so forth. So that's what some of the terms look like. Now notice that this time we have in parentheses an x minus 4 in each of our terms. So this would be a polynomial or a power series that we would say is centered at 4. Okay? Now to find the interval of convergence, you're going to start by taking the limit as n goes to infinity of our nth plus 1 term over our nth term. So that knocks out our alternating piece, and this is going to become an n plus 1 factorial. This is going to become an x minus 4 to the n plus 1 over a 3 to the n plus 1. And we're dividing that by n factorial, x minus 4 to the n over 3 to the n. So if we multiply by the reciprocal, then this fraction flips over and becomes a 3 to the n over n factorial x minus 4 to the n. And I'm going to break up all of these n plus 1's. So n plus 1 factorial is n plus 1 n factorial. Then we'll get an x minus 4 to the n and an x minus 4 to the first over 3 to the n times 3 to the first. And all of these are being multiplied. So the n factorials cancel, the x minus 4 to the n's cancel, the 3 to the n's cancel, and what we're left with is the limit as n goes to infinity of an n plus 1. We have an x minus 4, and we have a 3. Now as n goes to infinity, the only variable here is the n. The x is acting like a constant here. So the n is going to blow up and make all of this go to infinity, and infinity times a constant is going to stay infinite. So this is actually infinity. And that's not going to be less than 1 unless you look at this center point. Possibly convergence could happen at that center point. So this will diverge always, except possibly at x equals to 4. So if you go back to this series, look at what happens if you plug in 4 for x. This term goes to 0. This term goes to 0, and all these other terms that have those x minus 4's raised to a power go to 0. So all we're left with is a 1. So it will converge at 4, because we just go to 1. And what does that mean about your interval of convergence? Well, it's not an interval, it's just a number. It only converges at 4. So our interval would actually just look like 4, and I usually would wrap that in these curly braces to show that set. Okay? And remember here, your radius of convergence would just be 0 since you're convergent only at a specific number. Okay, the next example here, we've got an x minus 2 raised to the n plus 1 over n plus 1, 3 to the n plus 1. That x minus 2 is showing us that this is a power series centered at 2. And to find the interval of convergence, we're going to start with that limit. So the nth plus 1 term is actually going to make all of these n plus 1's turn into n plus 2's when I substitute in another n plus 1. So this will be x minus 2 to the n plus 2, n plus 2 times 3 to the n plus 2, all over x minus 2 to the n plus 1 over n plus 1, 3 to the n plus 1. So we're going to multiply by the reciprocal. So this will become this flipped over. So the n plus 1 and the 3 to the n plus 1 go on top, and the x minus 2 to the n plus 1 is on the bottom. And now when I break up this numerator, I'm just going to subtract 1 from the power and pull that aside. So x minus 2 to the n plus 2 is x minus 2 to the n plus 1 times another x minus 2. I'm trying to make it so that this power here matches this one so that they will cancel out. On the bottom, I have that n plus 2, and then this 3 to the n plus 2 I can break up into a 3 to the n plus 1 times another 3. And that way these 3 to the n's cancel. So what we're left with is an n plus 1 over an n plus a 2, and we also have an x minus 2 over a 3. In the limit, as n goes to infinity, these n's are going to cancel each other out and go to a 1. So in our answer here, what we're going to have is just that absolute value of that x minus 2 over that 3 times this 1. And what we need is for this in absolute value to be less than 1 in order to converge by the ratio test. So here's what we have. Now what does that look like in interval notation? Well, you can first multiply that 3 across to the other side, and then what this means is that x minus 2 must be squeezed in between negative 3 and positive 3. And if I add 2 across, then that means x is in between negative 1 and positive 5. Now we're not done because we would need to find our endpoints and see what happens there. And notice over here that after I've multiplied that 3 across, this number over here is your radius of convergence. You want to get that x by itself without any coefficient in front of it or underneath it. So back to our interval, let's look at our two endpoints. So if I look at x equals to negative 1, then this series becomes negative 1 minus a 2, which is a negative 3 to the n plus 1 over n plus 1 times 3 to the n plus 1. And the 3 to the n plus 1's are going to cancel, but you'll still have that negative 1 to the n plus 1 left over. So this part cancels with this part, but we'll still have that negative still there, and it's still raised to an n plus 1 power. So does this converge? I'm going to be a little bit lax here on my proof, but hopefully by now you can see that this will converge because it's just the alternating harmonic. If you expand out some of the terms, then this is going to be -1 plus a half minus a third plus a fourth, etc. So this is the alternating harmonic series, which we've already proven using the alternating series test converges. So that means -1 worked, so we want to include that endpoint. Now let's look at x equals to 5. So what does this sum become? 5 minus 2 is 3, so the numerator is just 3 to the n plus 1 over n plus 1 times 3 to the n plus 1. And this time these cancel out exactly, and there's no negative left over. So this is just 1 over n plus 1. And that is just a version of the regular harmonic series. If n is 0, this is 1 plus a half plus a third plus a fourth. And we know that that harmonic series diverges because it's a p series with p equal to 1. So we don't want to include the 5, so our interval of convergence would be -1 with a bracket, comma 5 with a parentheses. Now, because power series are really just functions, they're just infinite functions, they possess characteristics similar to other functions. We can differentiate them, we can integrate them, just as a way of obtaining new power series from old power series. So here's a theorem. It's properties of a function defined by a power series. So if you have a function that is written by just a generic power series, so these are your coefficients a0, a1, a2, and then this one is centered at c, and it's just got these powers of x's. So this is like an infinite polynomial centered at c. If we know that it has a radius of convergence of r greater than 0, and it converges on the intervals c minus r to c plus r, then f is continuous, differentiable, and integrable, where the derivative would just be bring down the power n and subtract 1 from the power. Or you can take the derivative term by term. So the derivative of this term would just be a to the 1. This term would be 2a sub 2 x minus c to the first. The derivative of this term would be 3a sub 3 x minus c squared, and so forth. So you can take the derivative inside of your summation notation, or you can take your derivative term by term. So to get the integral, you're just going to integrate like you normally would. If you have an x raised to a power, you would integrate that by adding 1 to the power and dividing by the new power. So that's exactly what I did here. I took my x minus c and I raised the power by 1 and divided by that new power. Now I just noticed here there's a typo. This should be an x cubed, x minus c cubed over 3 factorial. So you can get that integral by integrating from your power series or integrating term by term. So this x minus c, when I raise the power, becomes a square over 2, which would be this term here. This one should become a cube over 3, and that was the typo. The constant term a sub 0 just gets that x minus c in there, and just like with all indefinite integrals, you always have a plus c on the end. So this will have a plus c as well. Okay? Now the radius of convergence for the series obtained by differentiating or integrating a power series will stay the same as the original power series. So the radius of convergence doesn't change. The interval of convergence will only change possibly at the endpoints. Now here's something to kind of remember or memorize. When you differentiate, you will not gain endpoints. So if you are missing an endpoint with a strictly less than sign, you're not going to get it as a result of taking a derivative. When you're integrating, you will not lose endpoints. So if you start with a series that includes an endpoint with a bracket and then you integrate it, it's going to stay included for the integral. So let's practice this. Let's start with the power series f of x equals -1 to the n plus 1, x minus 5 to the n over n 5 to the n. So a few of these terms here, if n is 1, This is going to be even, so we'll just get x minus 5 to the first over 5. When n is 2, this is odd, so now it's going to be minus x minus 5 squared over 2 times 5 squared plus x minus 5 cubed over 3 times 5 cubed minus and so on. So that's kind of what the terms will look like. What we want to do first is find the interval of convergence of this series. So we look at our limit as n goes to infinity of a sub n plus 1 over a sub n. So the nth plus 1 term, disregarding the alternating piece, is going to be x minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1, and then we're dividing that by x minus 5 to the n over n 5 to the n. So if I multiply by the reciprocal, this flips over. So n 5 to the n over x minus 5 to the n, and then breaking up these n plus 1 powers, x minus 5 to the n times another x minus 5 over n plus 1, 5 to the n times another 5. So the 5 to the n's cancel, the x minus 5 to the n's cancel. What we're left with is this n over this n plus 1, and then this x minus 5 over this 5. In the limit, the n's are going to act like an n over n, which goes to 1. So this is going to be 1 times x minus 5 over 5 in absolute value. And we need that to be less than 1 for convergence. So if I multiply that 5 in the bottom across, your radius of convergence here is 5. Your interval of convergence tells us initially that this is going to be x minus 5 squeezed in between negative 5 and positive 5. So when I add 5 across, this becomes a 0 and this becomes a 10. So now we need to look at those two endpoints, 0 and 10. So if I let x be 0 up here, then this series becomes negative 1 to the n plus 1. 0 minus 5 is going to be a negative 5 to the n over n times 5 to the n. So first of all, the 5 to the n's are going to cancel, but I still have that negative 1 to the n in there. So I'll have a negative 1 to the n plus 1 times a negative 1 to the n over n. And if you look at those powers, we can go ahead and combine these a little bit. This is like a negative 1 to the 2n plus 1 over n. And just a little scratch work here. Negative 1 to the 2n plus 1 is negative 1 to the 2n times a negative 1 to the first. And 2n is always even, so this will always become positive. So we're just left with a negative 1 on top, raised to the first power. So this series right here is really negative 1 on top over n. Does that converge or diverge? It's going to diverge because it's just negative 1 times the harmonic series. It's not alternating because it's not negative 1 raised to a power. It's just negative 1 over n. So it's negative 1 times the harmonic series, and a constant times a series is going to stay the same convergence or divergence of the original series. So this diverges, so we don't want to include the 0. So let's see what happens at 10. If I plug in 10, I get negative 1 to the n plus 1. 10 minus 5 is 5, so this will be 5 to the n over n 5 to the n. So these guys cancel. And now you do have that alternating negative 1 on top. So this is going to converge because this case is the alternating harmonic. So that means I do get to include the 10. So my interval of convergence is going to be parentheses around the 0 and a bracket around the 10. Okay? Now what we're going to do with this is now we're going to take the derivative of this power series and see what that tells us about the interval of convergence. So if we start with this original power series, to take its derivative, you're going to take the derivative using your normal rules. And the only variable here, if you think of this as a polynomial in terms of x, are these x's. So how would you take the derivative of x minus 5 raised to the n? Well, that's just a chain rule with a power involved. You bring down the power and then you subtract 1 from the power. The n and the 5 to the n in the bottom are just constants, so you're not going to do any derivatives of those. You're just doing the derivative of the x part only. So initially, if this is our original function f, then f prime of x is going to look like negative 1 to the n plus 1. I bring down the power n, and I subtract 1 from the power, and I'm still dividing by that n and that 5n, so these n's are going to cancel out. So this is going to be the series negative 1 to the n plus 1, x minus 5 to the n minus 1 over 5 to the n. And if you expand that out a little bit, when n is 1, this is even, so this will be positive. This will be to the 0 power, so it goes to 1, and we just get 5 to the first on the bottom. So this is just going to be a 1/5. When n is 2, this is now odd, so we have a subtraction, and we get an x minus 5 to the first power over a 5 squared. Then we're going to go back to plus, and then this will be x minus 5 squared over 5 cubed, and so forth. And if you look up here, how we originally wrote this out, what would the derivative of this be term by term? Well, this first derivative is like an x minus 5 over 5. So the derivative is just going to be the 1 over 5 that we would get, and this x goes away. When I bring down the 2 here, it cancels with this 2, so I'm just left with an x minus 5 over 5 squared. And for this term, I bring down the 3, which cancels with the 3 in the bottom, so I'm left with an x minus 5 squared over 5 cubed, which is exactly what we're getting right here. So same answer, whether you do it term by term or with your power series notation. Now the interval of convergence of the original series was 0 to 10. So we can check both of those endpoints again. The nice thing about power series and derivatives and integrals is you're going to maintain the same interval of convergence except possibly lose or gain endpoints. So we need to look at our two endpoints again. So at 0, into this formula now, the derivative formula, this series would become negative 1 to the n plus 1. 0 minus 5 is going to be a negative 5 to the n minus 1 over 5 to the n. So breaking this up a little bit, we're going to get negative 1 to the n plus 1. We're going to get a negative 1 to the n minus 1 from just the negative part. And then I'm going to get a 5 to the n minus 1, which is like a 5 to the n and a 5 to the negative 1. These will cancel. If you look at those powers, this is going to be n plus 1 plus an n minus 1. When you add n plus 1 and n minus 1, you get 2n, which is always even. So negative 1 to the 2n is always positive 1. So these guys sort of cancel each other out, and 5 to the negative 1 is just 1/5. So this is the series from 1 to infinity of 1/5, which means when n is 1 you get a fifth, when n is 2 you get a fifth, when n is 3 you get a fifth, and so on. Does that converge? No, it diverges, because your nth term is always a fifth, and your nth term needs to be 0 to satisfy that nth term test for divergence. So this diverges by the nth term test. Now what I just did here is actually extra work, because what we said earlier up here in the previous page is that when you differentiate, you will never gain endpoints. So I already knew that 0 didn't work for the original function, so in the derivative there's no way it's going to work for the derivative as well. So you really didn't need to check 0, but I just wanted to show you that it doesn't really work even if you did try it. So I'm not going to gain 0 when I take a derivative. I could potentially lose the 10. So we do need to check the 10. We're checking it into this derivative formula over here. So when I plug it in, I'm going to get negative 1 to the n plus 1. 10 minus 5 is 5, so this is 5 to the n minus 1 over 5 to the n. Breaking that up, that's going to give me 5 to the n times 5 to the negative 1 over 5 to the n, so these cancel. So this is going to be the series that alternates negative 1 to the n plus 1 over 5. So when n is 1, this is a fifth. When n is 2, this is minus a fifth. When n is 3, it's plus a fifth, minus a fifth, and so on. Does that converge? No. It diverges again because the nth term is 1/5 every time. So the nth term isn't going to 0. So both of these diverged, which means my interval of convergence for f prime of x is going to be just 0 to 10 with parentheses. All right, now we want to find the power series for f double prime of x and the interval of convergence for f double prime of x. So let me copy our first derivative power series, which was up here. So negative 1 to the n plus 1 and then we got x minus 5 to the n minus 1 over 5 to the n. And expanded out, that was 1/5 minus x minus 5 over 5 squared plus x minus 5 squared over 5 cubed, etc. So the second derivative, we're just going to take the derivative again. Using just the power rule here on our x part only. This 5 to the n in the bottom is going to stay put. It's like a constant. So the derivative of x minus 5 to the n minus 1, you bring down your power, so this will be an n minus 1, and then the new power you subtract 1, so this will become an n minus 2. So if I expand that out, when n is 1, we're just going to get 0. When n is 2, this will be negative. This will become a 1, and when this is 2, this will go to 0. So the top is just a negative 1, and we'll get a 5 squared on the bottom, which is exactly the derivative of this term right here. This term went to 0. When n is 3, we're back to a positive. 3 minus 1 is 2, and we'll get an x minus 5 to the first, and we'll get a 5 cubed on the bottom, which is exactly the derivative of this term. You bring down the 2, you subtract 1 from the power, and the bottom stays the same. So this is going to continue. So here's our power series for the second derivative. And remember, the interval of convergence for the first derivative was 0 to 10. So that forces the interval of convergence for the second derivative to be 0 to 10 as well, because you can't gain any endpoints when you take a derivative. We won't gain any of the endpoints every time we take a derivative. And since both of them are already not included, I can't lose them because they're already lost. Okay? All right, now let's try an integral. So we need to recall what the power series was for the original function f. So that was the series from 1 to infinity of negative 1 to the n plus 1 with x minus 5 to the n over n 5 to the n, and the original interval of convergence of the original function was parentheses 0 bracket 10. So now we want to integrate this. So the integral of f of x dx is going to be our constant c. I'm going to put it in front this time because we'll have this infinite power series here. And then I'm going to integrate term by term here. So I'll get a negative 1 to the n plus 1, that stays put. The n and the 5 to the n stay put. And what do you get when you integrate an x to the n? Well, you're going to get an x, or in this case an x minus 5, to the n plus 1 over that new power n plus 1. if you want to expand out a few of the terms here, you can. This would be the constant c plus, and when n is 1, this is going to look like, this will be positive, and we'll get an x minus 5 squared over a 1 times a 2 times a 5 to the first. And then when n is 2, this will now be odd, so we'll be subtracting, and we'll get x minus 5 to the third, and we'll get a 2 times a 3 times this 5 squared, and so forth. And that's exactly the integral that you would get if you integrated each of these term by term. For example, this term here, you would add 1 to the power, so it would become a cube, and on the bottom you'd get 2 times 3 times 5 squared, which is exactly what we got right here. Went to a cube over 2 times 3 times 5 squared. So there is our integral. And now for the interval of convergence. For integrals, remember that you won't lose any endpoints. So we're not going to lose the 10 at all. So I don't really even need to check it. I'm not going to, won't lose x equals to 10. So that's going to stay included. Therefore, I only need to check x equals to 0. So we're going to plug it into this right here. Now the c really isn't going to affect the convergence or divergence because it'll just be a constant added to whatever this sum goes to. So I'm really only looking at the convergence of the series part. So let's plug in 0 for this x. So we'll get negative 1 to the n plus 1. 0 minus 5 is negative 5 to the n plus 1. Over n, 5 to the n times n plus 1. And I'm going to do a little bit of simplifying here to get a better feel for what this looks like. The negative 1 I'm going to pull out, and it's raised to the n plus 1. And then the 5 to the n plus 1 is really a 5 to the n times a 5. So the 5 to the n's cancel, and negative 1 times negative 1 to the n plus 1, both of those are raised to the same power. So it's like a negative 1 times a negative 1 raised to the n plus 1, and that's just 1 to the n plus 1, which is just 1. So these two cancel each other out. So this is the series 5 on top over n times n plus 1. And that's acting like a 5 over an n squared. So that's going to converge. I'll let you do the formal proof here, but it's going to converge by a limit comparison test to 1 over n squared. It's acting like a p-series because you've got that n squared on the bottom and a constant on the top. And I'll let you do the actual limit, but you would just do this 5 over n times n plus 1 divided by 1 over n squared, take the limit, and show that you get something greater than 0, which you will. So that means it does converge at 0. It already converged at 10, so our interval of convergence is now going to include both endpoints, 0 and 10. Right, for our last example, we have a function y equal to the sum from 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. And we want to show that that is a solution to the differential equation y double prime plus y equals to 0. Okay, let's write out what some of the terms look like. So we've got y equals the sum from 0 to infinity, negative 1 to the n x to the 2n over 2n factorial. So when n is 0, all of these go to 0. On the bottom we get 0 factorial, and powers of 0 go to 1. So this whole first term is just a 1. When n is 1, this is odd. So we'll have a negative, and then we'll get minus an x squared over 2 factorial. When n is 2, this will be even, so we're positive, and we'll get an x to the 4th over 4 factorial. When n is 3, we'll get minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc. So y prime is going to be the derivative of that. Now, on this one, I think it's easiest to just look in terms of the terms here, not even bother with the summation notation. So if you take the derivative of these going term by term, this one is going to go to 0. When I bring down the 2, it'll cancel out the 2 in the bottom, just giving me a minus x. When I bring down the 4 here, it'll cancel out the 4, but I'll still have 3 2 1 or 3 factorial in the bottom. So this will become an x 3 over 3 factorial. And then the next term, when I bring down the 6, the power goes down by 1, and I lose the 6, but I keep the 5 factorial. And when I bring down the 8 here, same idea. Now I have x to the 7th over 7 factorial. So here I had all even powers. When I take the derivative once, I have all odd powers. Now we want the second derivative right here. So let's see what that would look like. The derivative of negative x is negative 1, plus, when I bring down the 3, it cancels with the 3 out front, but I'll still have a 2 factorial in the bottom, and the power goes down by 1. Over here, I bring down the 5, so this goes down to a 4 factorial, and the power is x to the 4th, plus, bring down the 7, so I'm left with an x to the 6th over 6 factorial, and so forth. So you'll see that these two match, actually, except for the signs are opposite. We have all even terms again, but the signs are different. So that is exactly why when we do y double prime plus y, what's that going to be? Well, it's going to be all of these terms for y double prime plus all of these terms for y. And since they are exactly the same terms but always opposite in sign, they're all going to cancel each other out all the way to infinity. So this will cancel with this with this, this with this, this with this, and so forth. So they all cancel, and that's why you're going to end up with 0. So that's our proof. Now, just as a little side note here, can you think of a function that would satisfy this differential equation? Imagine the cosine function. Its first derivative is minus sine of x. Its second derivative would therefore be minus cosine of x. So if I plug in for the second derivative minus cosine x, and for y I plug in the original cosine x, these do cancel out, giving me 0. So what it turns out to kind of show us here is that this power series right here is actually the power series for the cosine function. And we're going to get to that in a few video lectures. Alright, that concludes our video lecture on power series and interval of convergence. Good luck.